Now let's look at a node analysis. So here's another example that we wish to use node analysis to figure out what I naught is. In this case, you can see the problem already give us ground, so we don't have to choose our own grounding. We could, of course, ground it in the middle points, but grounding at the lower point, the way that the problem expressed, is easier because we have two voltage sources. That makes the node voltage easier because this one's given. So let's give a name. Let's call this V1. Let's call this V1. Let's call this one is V2 right here. Now, this two nodes right here is given now. So the voltage here given is 12 volts, and here is 6 volts. All right, let's apply KCL at node 1. You can see we have 3 branches that connect to node 1. And what we have here, so let's give a name. Let's call this I1. This is I0, and this is I2. And you can see there's 3 currents. If I assume they all going out of the nodes, and they are all negative. If they are all negative, I can apply negative sign to everyone, and that becomes positive. So all the currents summed, all the currents that are going out is equal to 0. Therefore, what we have here is that we have V0, V1 minus that node, which is 12, divided by 2, the impedance of this element here, this 2. This one current coming out. The other current coming out is the one going through the 2 ohms here from V1 to V2. So the potential difference is V1 minus V2 divided by the impedance, which is 2. Finally, another current coming out of that node is the one that flowing through the 1 ohm resistor. And the potential difference across that resistor is V1 minus 6 divided by the impedance, which is 1. And that should be equal to 0. All the current summed up should be equal to 0. Now we apply, this is my equation 1. Now I apply KCL at node 2. We're going to get a second equation here. Once again, there are 3 currents. There's 3 currents here, and I still can assume the current is all just going away. I can still assume all the currents going away. And then the given current source is indeed going away. So we're going to sum all the currents that going out should be equal to 0. So we have the voltage difference across the capacitor is V2 minus 12 divided by negative J2, that's the impedance of the capacitor, then minus the current coming out, adding another current coming out, that is V2 minus 0 because the other side is grounded. So simply just V2 divided by the impedance of the inductor, which is J1. Now, finally, the current source coming out of that node is 2. That should be equal to 0. That's my equation 2. So now you can see the equation 1 and equation 2 both are involved. They're involved with V1 and V2, and we can simplify it, isolate V1 or V2 and solve them. So let's look at equation 1 and see. We're going to clean that up. We can combine the like terms. So we have 1/2 plus 1/2 plus 1. That's V1. So you can see we'll combine every terms with V1. And then V2, which is 1/2 times V2. Then we have, here we have 12 divided by 2. Here we have 12 divided by 2 is -6. Here we have another -6 right here. And adding them up and bringing to the other side of the equation, we have a positive 12 right here. So my first equation is simplified. We're going to do the same thing for a second equation. All right, now you see we notice a problem here. In the second equation, we're looking at the current coming out, we're looking at the current coming out, and looking at the current coming out, we ignore this current right here. There's a current coming out, this branch. So there should be 4 branches. And you can see, as we assumed, the I0 is coming into the nodes. So I certainly would have to say, this one I'm going to add currents, because I assumed that all the current coming out is positive now. Coming in should be a negative. That is V1 minus V2 divided by 2. So it should be 4 branches. And so now you can see all the sign that related with V2 is positive, so I'm going to keep that way. And therefore, this -1/2 of V1, then plus, now I'm going to combine all the terms with V2. So we have 1/2 minus (1/2) J. Now remember, if we put a J, let's J times J and times J, that actually J times J is -1. So that's actually change it to positive, and J disappears because J times J is just a -1. That's term. And then we do the same thing here. We have a plus -J. So this is a J1, J times J, J times J, J. That gives us a -1 here. So -1 V2 is equal to J6 minus 2. So this 2 goes to this side, this 2 goes to the other side. And then we have 12 divided by J2, bring to the other side, that makes it to J6. So now we actually simplified both equations, and we can do either substitution or any method. So I'm going to actually look at from the second equation, And look at from second equation. And to isolate V2, so from second equation here, oh, I'm sorry, from first equation here, V2 is equal to, look from here, V2 is equal to 4. If I multiply by 2 on every one here, so we have 4 V1 minus 24. Now I can put this into equation 2. So we have negative 1, equation 2 become negative half times V1. We're going to carry that. But we're going to substitute every V2. And here, plus 1/2 minus half J. We're going to combine the 1/2 J, positive 1/2 J and negative J, that become negative half J, times V2. And V2 is 4V1 minus 24. And that is equal to J6 minus 2. So now you can see this equation eventually contains only V1. V2 is substituted. And so we just need to simplify it, clean up, and find V1. So let's carry that. 1/2 of V1 plus, we're going to multiply that 4V1 times 1/2, that becomes 2V1. Then minus 2 JV1. And then we're going to use the negative 24 multiplied by the half. That is equal to positive a negative 12. And plus J12. That is equal to J6 minus 2. So we have all these V1s. We gather them up. We have 3/2 V1 minus J2 V1 that is equal to, I'm going to bring everything that known to the other side. So we're going to have 10 minus J6, 12, positive 12 minus 2 is equals 10, negative J12 plus J6 equals negative J6. So eventually V1 is equal to 10 minus J6 divided by 3/2 minus J2. So up to that point, again, we can make a phasor. We can change the numerator to phasor, denominator into a phasor, and then that is easier way to do it. So we have the magnitude to be 4.66, and the phase angle is the difference between the numerator and denominator's phase angle. That ends up to be 22.8 0.17 degrees volts. Now, because we know we're going to actually adding something, so this one here eventually we can still express that into a rectangular expression. So 4.66 times cosine 22.17, that gives you a real part, and that is equal to 4.32. And then the imaginary part is 4.66 times sine of 22.17. That gives us J 1.76. Now I'm doing this so that later on we need to add V1 to some numbers. So we need to do addition or subtraction operation, and rectangular component is necessary. So therefore, V2 is equal to, remember we obtained the V2 is equal to 4V1 minus 24. So you can see now we multiply 4 to the real part and imaginary part. Then we need to subtract 24. By doing that, we're going to end up with a negative 6.72 plus J 7.04. And now we can convert it into a phasor expression, which is 9.73 times the phase angle is 133.67. Once again, just a reminder, the magnitude is equal to real part, is the real part the square root of the real part, which is 6.72, plus the imaginary part squared. And the phase angle is obtained by taking the tangent of that imaginary 7.04 divided by negative 6.72. That's just a reminder how we obtain the phasor expression. So finally, I0, let's look at the original circuit here. I0 is what we're interested in, and I0 is the node is the current going from node 1 to node 2 through the 2 ohm resistor. So I0 is equal to potential difference, which is V1 minus V2 divided by the 2. So finally, I0 is equal to V1 minus V2 divided by 2. Now, V1, V2, both voltages we have rectangular expression. So we're going to just use the rectangular expression because we're doing addition. So we have a V1 is 4.32 plus J 1.76, where V2 is negative 6.72, so that's plus 6.72, and then minus J 7.04, and divided by 2. Now you can see we can just combine the real part in the numerator and the imaginary part of the numerator. So we have 11.04 minus J 5.28 divided by 2. Now we're ready to sum everything and to make it to a phasor. So once again, the real part squared plus the imaginary part squared give us the magnitude, which is 6.12, and the phase angle is the inverse of tangent of the imaginary part divided by the real part. That gives us negative 25.56 degrees ampere. So this is the node analysis. Now if we recall, again, to summarize this analysis, we did exactly the same thing as we did for the resistive circuits. We define the nodes, we define ground, and then we give each node a node voltage. Then we solve for the unknowns by using KCL.